In this video, I will discuss the Stern-Gerlach experiment, focusing specifically on the possible incorrect interpretation of this experiment. The Stern-Gerlach experiment has had a significant impact on the development of quantum mechanics and is employed as undeniable experimental proof for one of the most controversial statements of non-deterministic interpretation of quantum mechanics. This interpretation asserts the fundamental impossibility of defining an object property before an event of measuring that property occurs. It is important to emphasize that the results of the Stern-Gerlach experiment serve as a crucial experimental evidence for the development of modern quantum mechanics and quantum technology. In this presentation, I will demonstrate that additional, previously unaccounted for effect should be considered in a correct interpretation of the Stern-Gerlach experiment. Most significantly, I will show that the result of Stern-Gerlach experiment can be adequately explained by solely employing the classical effect of quantum mechanics, thus avoiding the need to involve the non-deterministic interpretation of quantum mechanics. So, what are the findings of the Stern-Gerlach experiment? The experiment measures the spin distribution in atomic gas, where each atom possesses an one unpaired electron and therefore carries a spin. The gas itself is not magnetic and there is no preferential direction. Consequently, it was expected the spins would be distributed equally in all directions. The measurement results were surprising. Instead of being distributed in all directions, the spins were found to be distributed only along two directions, up and down. It was an even more surprising result, that is a slight modified second measurement again revealed only two directions of spin. However, for the second measurement method, the direction differed. This time, the spin orientation were observed to be left and right. This indicates that the atomic gas does not inherently possess a defined distribution of spins. Instead, the spin distribution assumes a specific form only when a measurement of the spin distribution is conducted. This event is often referred to as the collapse of wave function. The specific spin distribution is not fixed and can vary for different types of measurements. Based on the result of this experiment, the foundation of non-deterministic quantum mechanics were established. So why, as a result and correct interpretation of a 100-year-old experiment, important now? The significance lies in the substantial impact on the future development of physics and technology. Modern physics is firmly rooted in quantum mechanics. The type of quantum mechanics, whether correct or incorrect, that will be utilized for future research greatly influences our success in uncovering new physics and solving present unsolved mysteries, such as the nature of dark matter and dark energy, and determining methods for interstellar travel. Currently, there are two interpretations of quantum mechanics, non-deterministic and deterministic. Even so, it is deterministic. The deterministic or Einstein interpretation still relies on probabilities and wave functions. However, probability is well defined for an object at all times. On the other hand, the non-deterministic or Copenhagen interpretation of quantum mechanics defines an object property only when it is measured and the wave function collapses. Otherwise, an object exists in superposition of states and therefore having superposition of its possible properties. The deterministic interpretation strictly respects all conservation laws and all symmetries of space-time. In contrast, in the non-deterministic interpretation, these principles can be compromised. Present-day data technology has reached such limits as quantum mechanics began to play a significant role. If true quantum mechanics prove to be deterministic, we can proceed to enhance our current data processing technology, which relies on bits. However, if true quantum mechanics is non-deterministic, technology will need substantial modification. Qubits would replace bits, and new quantum data processing algorithms would need development. Each pathway for the development of future data processing technologies requires significant resources and time. Therefore, the choice of a correct path is crucial. That is why, as a result and correct interpretation of Stern-Gerlach experiment important now. Why should researchers in the optical field be interested in the Stern-Gerlach experiment? It is because an optical experiment similar to Stern-Gerlach experiment could provide a definitive resolution to the century-old unresolved problem regarding the deterministic or non-deterministic nature of quantum mechanics. A photon is the simplest existing elementary particle in our universe. To test the fundamental principles of quantum mechanics, it undergoes neither weak or strong interaction and lacks of rest mass, indicating no interaction with the Higgs field. It has a simple structure consisting of easily measurable components of electrical and magnetic fields. The photon is an extremely well understood and measured object in physics. For photon physics to exhibit non-deterministic behavior, the polarization of phase of the photon should be different for different type of measurements. I myself did numerous optical experiments utilizing long, short, and ultra-short optical pulses, employing various optical interferometers. Through these experiments, I have never observed variation in photon polarization of phase between different measurements. Consequently, my current perspective is that photon physics operate on deterministic principles. However, I remain open to the possibility that the optical experiment akin to the Stern-Gerlach experiment could potentially change my viewpoint. Next, I would like to briefly mention the historical debates sparked by the results of Stern-Gerlach experiment. The non-deterministic principle of quantum mechanics, which suggests that object properties remain undefined until measured, has faced severe criticism from the majority of prominent scientists due to its contradiction with established conservation and symmetry laws in physics. Einstein's famous statement, "God does not play dice with the universe," was directed specifically at the non-deterministic interpretation of quantum mechanics, and not at quantum mechanics as a whole. To challenge the non-deterministic interpretation, the father of quantum mechanics, Schrödinger, proposed the following thought experiment, known as the Schrödinger cat. A cat is confined within a room containing radioactive materials, which has the potential to kill the cat. As there is no means to observe the cat's state from outside the room, according to the non-deterministic principle, the cat exists in a simultaneous state of being both alive and dead, or in a superposition state encompassing both possibilities. Such a state appears entirely nonsensical. I understand that the cat lovers might prefer that a less beloved creature, such as a bacterium, we use in such thought experiment, but anyway. Another thought experiment, known as the Einstein-Podolsky-Rosen paradox, involves two strongly interacting particles whose properties are locked to each other or entangled. When the property of one particle is measured and thereby defined to a certain value, The corresponding property of the second particle is simultaneously defined and fixed. Consequently, an event occurring at the location of the first particle appears to instantaneously influence the second particle, which may be positioned at a different location, similarly defying the speed limit of light. Such an outcome violates the principle of causality and is fundamentally impermissible. Next, I will explain the specifics of the Stern-Gerlach experiment. I should acknowledge that when the experiment was initially conducted, the concept of spin was not yet known. In fact, the experiment itself played a pivotal role in the discovery of spin. The notation of the spin was first introduced by Schrödinger and later substantiated in Pauli and Dirac equations. The image from Wikipedia depicts a rather intricate magnet used to create a homogeneous magnetic field. Silver atoms passing through this field are deflected based on their spin. Instead of observing a line representing a homogeneous spin distribution, two distinct dots were detected, corresponding solely to the up and down directions of the spin. When the magnet is rotating by 90 degrees, the position of the spots also rotated by 90 degrees, indicating in this instance only spin directions to the left and to the right. A magnet of such complexity is employed because the spin experiences a mechanical force only within a gradient of magnetic field. Utilizing a gradient of magnetic field is the only feasible method to separate atoms with different spin directions. In fact, the result of the measurement of the Stern-Gerlach experiment is not just the two simple dots. This image is from the original paper by Stern and Gerlach, where two separate lines were detected. Still, two lines correspond to only two spin directions. Now, I will explain why the incorrect interpretation of the Stern-Gerlach experiment was accepted for a long time. To grasp this, it's crucial to understand all the effects the spin experiences in magnetic field. Of which there are only three. The first effect is mechanical force experienced by spin in gradient of magnetic field. The second effect is spin precession around the magnetic field, and the third effect is the alignment of spin along the magnetic field. The spin precession and spin alignment do not generate any mechanical force. Therefore, these effects were completely disregarded in the classical incorrect interpretation of the Stern-Gerlach experiment. However, this assumption is fundamentally flawed, and it is the reason for the incorrectness of the classical interpretation. Despite not producing a mechanical force, the spin alignment is the key influencer and plays a critical role in this experiment. This animation illustrates the correct interpretation of Stern-Gerlach experiment, considering both the force due to the gradient of magnetic field and the alignment of the spin along the magnetic field. The magnetic field, depicted by green arrows, exhibit a gradient that transitions from upward direction on the left to downward direction on the right. Spin generated by the gun flows through the gradient of the magnetic field towards the detection screen. Spin, positioned slightly left of center, aligns the spin upwards because the magnetic field in this region points upward. Consequently, the gradient deflects them farther to the left. As all atoms quickly align the spin in the same upward direction, they experience the same force and converge into one point on the left. Conversely, atom initially positioned slightly right of center aligns the spins downwards because the magnetic field direction in this region is downward. This downspin atom experiences an opposite force in the gradient and converge into one point on the right. Therefore, the experiment yields two detected points on the left and right, mirroring the observation in the real experiment. Let us consider the result of 90-degree rotation of the magnet. As magnet rotates, both the direction of magnetic field and direction of gradient are also rotated. After rotation, the magnetic field is directed to the right at the top side and to the left at the bottom side. Atoms, initially positioned slightly upward of center, align the spins to the right and experience a force in upward direction in the gradient, converging into one point at top. Conversely, atom initially positioned slightly downward of center aligns the spin to the left, experience force in the downward direction, and converge in one point at the bottom. Once again, the experiment yields two detected points, this time at the top and bottom, which again exactly mirrors the observation in the real experiment. The usage of spin alignment effect perfectly explains all the result of the Stern-Gerlach experiment, without need of usage of principle of non-deterministic quantum mechanics. The spin distribution in atomic gas can assume its natural symmetrical form when the spins are evenly distributed in all directions. Measurement is influenced by two effects: the spin alignment and spin deflection. During the first measurement, the spin are aligned up and down from the initial even distribution. Subsequently, the spin are deflected to the left and right according to the spin direction. The measured result reveals two horizontal dots. Upon rotating the magnet 90 degrees, the spin aligns to the left and right. Following this, the spin are deflected to the up and down directions. The measurement result reveals two vertical spots. This perfectly explains all the features of the Stern-Gerlach experiment using only classical effects. In conclusion, the classical interpretation of Stern-Gerlach experiment based on non-deterministic quantum mechanics is found to be incorrect. The previously unaccounted for effect, spin alignment along magnetic field, must be incorporated into the correct interpretation of the experiment. Once considered, all results and features of Stern-Gerlach experiment are perfectly described using only classical effects. The Stern-Gerlach experiment does not support the principles of non-deterministic quantum mechanics, suggesting that deterministic quantum mechanics may govern our universe. Consequently, it is highly plausible that our future technology will be based on bit processing, rather than on qubits manipulated by quantum processing technologies.